Hi everybody, welcome back to Environmental Organic Chemistry with Dr. Lisa. Today I'm going to do problem 20.4 from the Schwarzenbach et al. Textbook. This is a problem about air-water exchange, experimental determination of the total air-water exchange rate for two chlorinated hydrocarbons in the river. So the chlorinated hydrocarbons we're going to deal with are tetrachloroethene or ethylene, which we call PCE, and 1,4-dichlorobenzene, which would be para-dichlorobenzene. So these two chemicals were measured in a field study in the River Glatt in Switzerland, and they were measured at 4 locations along a river section about 2.5 kilometers in length. Any input of water and chemicals can be excluded in this river section. The average depth is 0.4 meters, and the mean flow velocity of the river is 0.67 meters per second. And those two things remain constant or fairly constant. Now, usually when you're measuring the flow of a river, you're measuring it in something like cubic feet per second, CFS. But here they have taken that kind of flow and converted it into a linear flow velocity. That's relatively unusual. Again, usually you'd get discharge, which is like cubic feet or cubic meters per second. But they have converted it into a linear velocity. The measurements were made in a way that a specific parcel of water was followed downstream and sampled at the appropriate distances. Calculate the mean total air-water exchange velocity, the VAW, of these two substances by assuming that exchange to the atmosphere is the only elimination process from the water and that the atmospheric concentrations of these chemicals are very, very small. So in other words, we can assume that there's no back diffusion of the chemicals back from the atmosphere into the water column. It's just a one-directional flow. So in our one box model, if we go back, go back to our box model. Remember we said that if we're in a one box model and we're expressing our mass balance as concentration versus time, dc dt, and we deal only with the volatilization flux, the flux is active over the entire surface area. Divide the surface area by the volume to get the concentration over here, and A over V becomes depth. So dc dt is equal to the K AW, the rate constant for the disappearance of the chemical due to volatilization, multiplied by its dissolved phase concentration. So the trick to this problem is to understand that when they say distance here, they're really not talking about distance, they're really talking about time. Because up here they say that a specific parcel of water was followed downstream and sampled at the appropriate distances. So really this distance can be converted into time. So let's do that. So this is distance in meters, and we have our velocity in meters per second. So if we take that distance and divide it by the velocity, we get time in seconds. So velocity is always in that cell. Use our F4 to put our little dollar signs there. And voila. Okay. And these are not really changing. So when we're trying to calculate dc dt is equal to a first order rate constant times the concentration. The easiest way to do that is to linearize it. So you calculate the log of concentration versus time. So let's do that. Equals natural log of this concentration. Boom. And then in theory, if we plotted this, we would get a relatively nice straight plot. And in fact, wow, look at that. That's pretty darn good. Doesn't get much better than that. Let's add our equation to this chart. And we get an R squared of 0.9997, which never happens, which is how you know that this data is baloney. This is probably made up data. I cannot imagine that anybody actually did this experiment and got anything as nearly as nice as this. Let's add the dichlorobenzene to this plot. Also add the trend line there. And again, R squared is 0.995. And just to be really, really annoying, I want to fix my axes so that this looks a little bit nicer. There we go. That looks lovely. Doesn't that look nice? It's so nice. Okay. And I mean, really, if I'm going to be anal retentive, I'll go over here and add a legend. There we go. Wow, so impressive. So this is log of concentration. and this is time in seconds. Okay, so let's see, where are we here? So in case you kind of got lost as to where we are, here we're talking about a pseudo first order reaction. So dA, here we're using the letter A, whatever dC dt is equal to minus K times the concentration of A. And so we can integrate both sides and come up with this equation. A at any given time is equal to the initial concentration of A times e to the minus kt. If we take the natural log of both sides, then the natural log of AT over A naught is equal to minus KT. So this is your time in seconds. This is your natural log of C. And so the slope here is the K value. So we just want to calculate our slope. And of course, there's multiple ways to do that. We could read it off the plot. You can see that according to the plot, these are both minus 0.002. But let's do it a little bit more rigorously and calculate it this way. Slope is y comma x. Same thing here. That's not right. That's not right at all. My little equation's getting in the way. There we go. And then we just got to make sure we got time here. There we go. All right, so here's our rate constants. So this is K AW. So that's our rate constant. Now what we want is VAW. If you remember how we got that, we did the same thing. Go right back up here. Our KAW is what we got from the mass transfer coefficient divided by the depth. So to figure out the mass transfer coefficient, we just have to multiply this first order rate constant by the depth. So our VAW is now equal to this times the depth, which is 0.4 meters. Sign's not very important here. So about 7 times 10 to the minus 5, and our units here were in seconds. And our depth was in meters. This is meters per second. Now, you may remember, maybe not, from the air-water exchange lecture that we had this equation, 1 over VAW is equal to 1 over VW plus 1 over VA times the Henry's law constant. And we said that's one way of determining the overall exchange velocity by calculating the mass transfer coefficient in the water phase and in the air phase and using Henry's law to convert it into a mass transfer coefficient across the entire air-water exchange interface. And we said that the VA, the rate of mass transfer in the air side, is usually somewhere around a centimeter per second. This is approximate. It's not taking into account wind speed. So this is sort of a time average over sort of a normal day with a normal wind speed. And the mass transfer coefficient for movement through the water phase is slower by 3 orders of magnitude because the water is much more viscous. So these were expressed in centimeters per second. These are in meters per second. And so it might be useful for us to just convert this to centimeters per second, just so we can have everything in the same units. So if this is meters and I want centimeters, I need to multiply or divide. I need to multiply this by 100. Oops, multiply. And I'm also going to change the sign here. Multiply this by 100. So there's our coefficients in centimeters per second. And then I want to ask the question, like, does that match what I would get if I used this formulation? So I have my Henry's law constants here. So let us then use those to calculate. So this is VAW that we might call experimental, because this is based on some data that was taken out in the real world. And then let's say we calculated a VAW value that was VAW that is like theoretical. And I'm going to leave myself a little room here to do some math. Okay, so I know that 1 over VW doesn't change. It's the same for both, and that is equal to 1 over the 1 times 10 to the minus third. So it's 1,000. Instead of centimeters per second, this is now seconds per centimeter, just to be right. Okay, and then the 1 over VAW will be different for each of these because they have different Henry's law constants, VAW. So that is equal to 1 over parentheses the VA, which is 1 centimeter per second, times the times the Henry's law constant up here. So this is, again, seconds per centimeter. And so 1 over VAW is the sum of these two. That plus that. Oops, did I get that right? Do it again. That plus that. Oh, yeah, sorry, I screwed it up. Here we go. Try that one more time. B56 plus this. And you can see this is 1,000 and this is 1.5. So the 1,000 is much more important. So the 1 over VAW is about 1,000. Something similar going on here. That plus that. So they're very, very close. This is just 1.01 versus 1.00. So VAW is 1 over this. In centimeters per second. And then, let's, instead of scientific, let's give that regular number notation so we can compare it. So we calculated 0.007, and here we're getting 0.0009. So quite a big difference, although here it's a little closer, 0.0001 versus 0.0009. We are off by about an order of magnitude. Sorry, that's not right. Sorry, 0.006. So we're off by about an order of magnitude versus the theoretical, but at least we're in the ballpark. And I'm not too concerned about this because, this is experimental. We could be at a much lower wind speed, or actually would have to be a much higher wind speed because the mass transfer is moving more quickly. So it doesn't disturb me too much. The other thing that's going on is that the river is flowing. And the flow of the river introduces turbulence, which drives mass transfer. So the fact that we get a faster mass transfer coefficient in our real experimental numbers doesn't scare me too much. But it's kind of nice to make that comparison. So to two significant figures, these two compounds would have very close to the same mass transfer coefficient, at least when you use the theoretical application, because you notice VW is the thing that's really driving the overall mass transfer. If the Henry's law constants were much smaller, if KAW is smaller, then this whole term is larger, and this term starts to drive the mass transfer coefficient much more importantly or rapidly. And then, so that's true, on a theoretical basis, they would have virtually the same mass transfer coefficient because they have similar Henry's law constants, and they're both quite low Henry's law constants. Well, actually, they're quite high Henry's law constants. And so as a result, VW is really driving the overall mass transfer. But even in the experimental data, they're pretty close. They have pretty similar mass transfer coefficients. The dichlorobenzene is moving a little bit more slowly. Remember, this has units of a velocity, centimeters per second, so it's moving slightly more slowly than the PCE. That makes sense because dichlorobenzene is a little bit of a bigger molecule, so it would have a slower diffusion coefficient, slower mass transfer overall. Now, another thing that we might want to do just for kicks is we might want to calculate we might want to calculate our half-life with respect to volatilization, just for kicks. So we'll call that T1/2, and that would be the natural log of 2 divided by our rate constant, our KAW. So this is in seconds, because our KAW up here had units of 1 over seconds. So that's kind of weird in terms of units. It's hard to think about 3,000 seconds, but maybe we could divide that by 60 seconds to give us minutes. So 65 minutes. So about an hour. So this is minutes. So half-life is about an hour. So this would be true because these compounds have fairly high Henry's law constants and they're Kw or Vw dominated. This would be true for any compound that falls within that range where Vw dominates, where the Henry's law constant is fairly high, such that this is small and not important. So that gives you a good idea of what's going on for a wide range of chemicals that are water side dominated. Their half-life, and this is with respect to a system where the depth is only 0.4 meters. This is not a very deep system, but in this not very deep system, the half-life is pretty fast. So it gives you an example of how volatilization can be a very, very important loss process for many chemicals in the environment.